Alright, well here's a video on the finding of eigenvalues, those lambdas, of a square matrix A. You might have noticed at the end of last class I set up the beginning of how to find the eigenvalues of a particular matrix, and that's by solving the following equation. You take the determinant of lambda times the identity matrix minus our matrix A and try to determine when this is equal to 0. You're going to solve this equation for lambda, and these values of lambda will be called the eigenvalues of matrix A. For example, say we're asked to find the eigenvalues, lambda, of this 2 by 2 matrix. So I've got A is this 2 by 2 matrix with the first row 2, negative 12, second row 1, negative 5. So since we're going to be taking the determinant of lambda I minus A, let's see what that is. Lambda times I, remember I is it'll be the 2 by 2 identity matrix here, and that's with 1s down the diagonal and 0s everywhere else. And if you're multiplying that by lambda, that means you have lambdas down the diagonal and 0s everywhere else. Alright, then from this we're subtracting A. Alright, subtract the corresponding entries. So you have lambda minus 2, first row, first column, 12, negative 1, and lambda plus 5. Right. And really, if you'd like to make that quick, just take the opposite of all the entries of A, negative 2, positive 12, negative 1, and positive 5, and then throw, lambda minus in front of the diagonal entries. Or lambda plus, technically lambda plus negative 2, lambda plus, negative 5. Alright, then we want to find the determinant of this and determine where it's equal to 0. Right, the determinant of this 2 by 2 matrix, is you do the little cross product, difference of the cross products, lambda minus 2 times lambda plus 5 minus 12 times negative 1. So you're getting here lambda squared plus 3 lambda minus 10, and then plus 12. So that's lambda squared plus 3 lambda plus 2. And then we're determining where is this, for what values of lambda is this equal to 0. So then you're solving, right, where is the determinant of lambda I minus A equal to 0? So lambda squared plus 3 lambda plus 2 equals 0. Well, your ability to factor things, now you could use the quadratic formula here. This is a quadratic equation in lambda, but you'll see we'll get higher degree polynomial equations. So your ability to factor things will be paramount here, very important. This factors to lambda plus 2 times lambda plus 1, and when that's equal to 0, well, when lambda is negative 2, or when lambda is negative 1. So one of them we'll call those lambda 1, negative 2, right, make that factor 0. And the other I'll call lambda 2, and that's negative 1, which made that factor 0. Either way, these numbers here, negative 2 for lambda 1 and negative 1 for lambda 2, these would be called the eigenvalues of matrix A. So there was an example with a 2 by 2. I have one more where there's a 3 by 3 matrix. So say we're asked to find the eigenvalues of the following matrix. Again, A here is a nice 3 by 3 square matrix. Got 2, negative 2, 3, 0, 3, negative 2, 0, negative 1, 2. And we wish to find, where is the determinant of lambda I minus A equals 0. So let's see what the matrix lambda I minus A is. So here's lambda I, again, lambda's down the diagonal, zeros everywhere else, minus A. And as I mentioned with the 2 by 2, you can just take the opposite of all these entries. So -2, +2, -3, +2, +1, -2, and just throw a lambda plus down the diagonals, right? Lambda plus -2, lambda plus -3, lambda plus -2. And there's your lambda I minus A. Lambda minus 2, 2, -3, 0, lambda minus 3, 2, 0, 1, lambda minus 2. Alright, now we wish to find the determinant of this and then see where is the determinant equal to 0. So the determinant of this matrix, I will do the cofactor expansion. This one's a nice simple one, because I can go down the first column. See, there are 2 zeros and only one non-zero entry. So the determinant of this matrix is, I'll take this first row, first column entry, lambda minus 2, multiplied by the minor. So get rid of the first row, first column, and it'll be a positive minor, right? This is an even position, first row, first column. So I just have lambda minus 2 multiplied by the determinant of this 2 by 2 matrix, lambda minus 3, 2, 1, lambda minus 2. Alright, so I'm going to keep this lambda minus 2 out here, and then the determinant of this 2 by 2 is lambda minus 3 times lambda minus 2 minus 2 times 1. Let me multiply this out, and I'm going to keep the lambda minus 2 on its own because we're trying to factor these eventually anyway, so we already have one factor. Let's see what this is in the brackets here. So that's lambda minus 2 multiplied by lambda squared minus 5 lambda plus 6 minus 2. That's lambda squared minus 5 lambda plus 4. And this factors even further as well, nice factorable quadratic, to lambda minus 4 times lambda minus 1. So the determinant of lambda I minus A is lambda minus 2 times lambda minus 4 times lambda minus 1. And we're setting that equal to 0. When is that equal to 0? Right. Well, that's equal to 0 when lambda is 2, when lambda is 4, and when lambda is -1. Right, so I'll call 2 lambda 1, 4 lambda 2, and 1 lambda 3. So here would be what they call the eigenvalues of that matrix A. And in the next video, we'll be finding eigenvectors corresponding to a particular eigenvalue.